Welcome to the deep dive. Today, we're jumping straight into recursion. It's a cornerstone concept in computer science.
It really is.
Yeah.
And sometimes a bit tricky to wrap your head around initially.
Exactly. So we've got these 10 core questions we're going to tackle. The mission for you listening: get a really solid grasp of recursion, sort of demystify it.
Sounds like a plan. By hitting these questions, we should make it much clearer.
Great. So let's kick things off with the absolute basic. What is recursion?
Okay, so simply put, recursion is basically when a function calls itself.
It calls itself.
Yeah, within its own code. It uses self-reference to solve a problem.
Okay. How does that actually work, though, the self-calling part?
Well, think of it like breaking a big problem down into smaller, identical versions of itself.
Right.
The function calls itself to handle those smaller bits.
Right. And then somehow pieces the answers back together.
Exactly. The solutions to the smaller bits are combined to solve the original, bigger problem.
Okay, but what stops it? I mean, if it keeps calling itself, couldn't it just go on forever?
Good question. That's where the base case comes in. It's absolutely vital.
The base case. What is that?
It's conditioned inside the function. When that condition is met, the function stops calling itself and just returns a result. It's the escape hatch.
So it needs that definite stopping point. Otherwise...
Otherwise, you get infinite recursion. We'll probably touch on that again.
Okay, makes sense. Now, we often use loops, iteration, for repetition. How is recursion different from, say, a for loop?
Right. Both do repetition, but in different ways.
Mm-hmm.
Iteration uses explicit loop structures for, well, whatever, to repeat code. Recursion does it via those function self-calls. It's a different mechanism for achieving repetition. Sometimes the recursive way feels more natural for certain problems.
Like what sort of problems?
Things with a naturally hierarchical or self-similar structure, like processing data organized in a tree. The code can mirror the structure.
Okay. You mentioned infinite recursion if there's no escape hatch. What actually happens then if you forget the base case or it never gets hit?
Well, that's bad news. The function just keeps calling itself, deeper and deeper. Each call uses up a bit of memory.
So it's a memory issue.
Precisely. It keeps consuming memory on something called the call stack until, well, the computer runs out. The program typically crashes.
Crashes. Okay, not ideal. So let's talk about that memory usage. How does recursion use memory compared to iteration?
It's quite different. Recursion heavily relies on the call stack. Every time the function calls itself, a new frame is pushed onto this stack. It holds the state for that specific call.
Like keeping track of where it is.
Exactly. Variables, return addresses, things like that. Iteration usually uses a more constant, smaller amount of memory. It just updates variables within the loop.
So more calls means a bigger stack. Are there common places where recursion is actually the preferred way? Examples?
Oh, definitely. We mentioned tree traversal. Also, algorithms based on divide and conquer, like merge, sort, or quicksort, they naturally break problems down recursively.
Yeah.
Calculating factorials is a classic simple example, too.
Right. And you mentioned visualizing this with the call stack. How does that help understanding?
It really clarifies the flow. Imagine stacking plates. Each function call adds a plate. When a function hits its base case and returns, its plate is removed. You can see the sequence, how deep it goes, and how results pass back up.
Okay, that visual helps. Now, I've heard about something called tail recursion. What's that about? Is it an optimization thing?
It is, potentially. Tail recursion is a specific case where the recursive call is the very last action the function performs. There's nothing else to do after it returns.
And why is that special?
Because some compilers or interpreters are smart enough to optimize it. They can essentially reuse the same stack frame instead of creating a new one for the tail call. Makes it as memory efficient as a loop.
Oh, interesting. So you get the recursive style without the stack buildup.
In theory, yes. But it's important to know not all languages or environments actually perform this optimization. You can't always rely on it.
Gotcha. So even with potential optimizations, deep recursion can still be an issue. You mentioned crashes earlier, Stack Overflow.
Exactly. The call stack isn't infinite. It has a size limit. If your recursion goes too many levels deep before hitting the base case, you exceed that limit, boom, Stack Overflow error. Program stops.
So there's a practical depth limit?
There is. It depends on the system and the language, but yeah, very deep recursion can be fragile.
Okay, let's try and summarize the key points from these questions then.
Sure. So recursion, function calls itself, needs a base case to stop. Uses the call stack for memory, which grows with each call.
Right, and that's different from iterations loops. It can be elegant for certain problems, like trees or divide and conquer.
But watch out for infinite recursion if the base case is wrong. and Stack Overflow if it goes too deep. Tail recursion offers potential optimization but isn't guaranteed.
Perfect. So, for you listening, maybe think about problems you encounter day to day. Are there anywhere breaking it down into smaller, self-similar parts might actually provide a really neat solution?
Or even just appreciating the hidden complexity, like how the call stack is working away behind the scenes whenever you run almost any program. It's fundamental stuff.
Definitely food for thought. Thanks for breaking that down.
My pleasure. It's a fascinating topic.